Hi everyone, welcome back to chemistry. In this video, we're going to start chapter 6, which is all about quantities in chemical reactions. So we talked about kind of chemical reactions more qualitatively, thinking about, what types of chemical reactions there are and how we can kind of distinguish them from each other based on, looking at the chemical equations. But what if we want to quantify, hey, how much of a product can I make? Or how many grams of this one substance do I need to react with this other substance in order to get this reaction to go, stuff like that. So we're going to get a little mathy, but that's okay because it won't be too bad. All right. So in order to talk about these kind of how we quantify these things in our chemical reactions, we need to know this special unit of measurement that we use in chemistry called the mole. And the mole is often referred to as the chemist's dozen. So the chemist's dozen. You might have heard of like a baker's dozen. This is like a chemist's dozen is the mole. But before we talk about the mole, I want to talk about a dozen. So when you go to the store, if you do eat eggs, right? Whenever you buy eggs, they're probably in a dozen, a pack of a dozen, right? Sometimes half a dozen. But when we say the term dozen, we know that means 12 of that thing, right? And usually we think of a dozen eggs because, or at least I do, because, that's what I'm buying most often in packs of a dozen. But anytime I hear the word dozen, I know it's 12 of anything, right? A dozen apples is 12 apples. A dozen cats is 12 cats. So it's similarly, one mole is always 6.022 times 10 to the 23rd of that thing. 1 mole of anything, right? 1 mole of eggs is 6.022 times 10 to the 23rd of those eggs. 1 mole of apples is 6.022 times 10 to the 23rd apples. So 1 mole is understood to be that many units. And there's actually a special name for this number because it's quite a mouthful to just say 6.022 times 10 to the 23rd. And that is Avogadro's number. We call that number Avogadro's number. That's named after the 19th century chemist Amedeo Avogadro, who kind of discovered this unit. And it's really important to just remember that 1 mole of anything is 6.022 times 10 to the 23rd of that thing. It could be atoms, right? It could be molecules you're looking at. It could be ions that you're looking at. Typically for this class, it's usually going to be atoms or molecules, but it could be anything. 1 mole of anything is 6.022 times 10 to the 23rd of that thing, or Avogadro's number of that thing. So why such a big number? Because I'm looking at this, right? Times 10 to the 23rd. That's a really large number, right? That's huge. That's 10 times itself 23 times 6.022. And so why is it so big? Well, that's because remember, these atoms, molecules, ions, they're really, really small. And so Avogadro said, look, it'd be really nice if I could figure out, hey, if I have 5 grams of copper, right? I'm not going to be able to see how many atoms. I don't have some kind of atom counter, to figure out how many atoms are in my sample of copper. So it'd be really nice if I could actually figure that out quantitatively, count how many atoms I have of copper in my 5-gram sample of copper. And that's where the mole comes in. So we needed a unit that could describe these really large amounts of atoms or molecules or ions of these tiny, tiny things. And that's where we came up with the mole. So we talked about unit conversions last week, and a little bit even in the beginning of the quarter. But it turns out we can actually use these unit conversions to convert back and forth between moles and something like atoms, molecules, or ions. And remember that I said that anytime we have some kind of equality, right, that equality can always be written as a conversion factor. And just to review, there are 2 conversion factors we can write from this equality. Now, what are the 2 of them? Yeah, we can write 1 mole on top, and it could be just, 1 mole of X, whatever you have, right? Apples, dogs, cats, I don't know, I'm thinking of animals. 1 mole of something, right, is 6.022 times 10 to the 23rd, atoms of X, for instance. This would just be an example. You could also write that with the 6.022 times 10 to the 23rd atoms of X on top and 1 mole of X on the bottom, right? And whichever one of these conversion factors you choose just depends on what your ultimate goal is to convert to, right? If I want to get from, moles to atoms of something, then I'm going to want to use one of those conversion factors in order to get atoms to be the thing I end up with, right? So you just get to pick and choose one of those. But you can always write 2 conversion factors for every equality. Okay, so that was just a little bit of a recap. But what does this mean in terms of converting between moles? In order to understand how to do this example here, because we are going to do that, I do want to take a quick side quest, and talk about moles in chemical formulas. Okay, so for instance, if we have say we have H2O, we're looking at that molecule. What I'm going to describe here is very weird at first, but you'll get used to it. So just hang in there with me. What I want to tell you is that 1 mole of this substance of water, 1 mole of water, contains 2 moles of hydrogen atoms and 1 mole of oxygen atoms. Within, right, 1 mole of H2O molecules. And that sounds really funky, right? How can there be 2 moles of something in 1 mole of, one other thing? Well, it's because we're looking now only at atoms rather than molecules, right? In one big molecule, 1 mole of my whole molecule, there are 2 moles of hydrogen and 1 mole of oxygen. So it's really weird, but you just have to kind of trust me on this one. So, and let's try this again, right? If we have something like, let's go CO2, right? In 1 mole of CO2, there are how many moles of carbon? Yeah, 1 mole of carbon. And how many moles of oxygen? Yeah, 2 moles of oxygen. Oops. 2 moles of oxygen. Per every 1 mole of CO2 molecules. Okay, now something like N2, which we're going to do an example with. We've got, 2 atoms of nitrogen. That's what that 2 is telling us, right? So that means we have 2 moles of N atoms, nitrogen atoms, in 1 mole of N2 molecules. I know, it's weird, you guys, but just trust me on this one. So anytime you see a chemical formula, you know how many moles of each atom are in that molecule or ionic compound or in your formula, okay? And that's given by those subscripts, okay? And again, remember, if you don't see a subscript, that just means there's 1 of that atom. Okay, so that was just a side note, so we can solve this problem here. So this says, for example, 1 N2 molecule contains 2 nitrogen atoms. Now, so what we want to know is how many nitrogen atoms are in 1 mole of N2. So this is a conversion problem. So for any of these problems, what I first like to do is I like to kind of think about a general problem solving strategy. So this is what I'm given, 1 mole that I have, 1 mole of N2. Oh, and I apologize, you guys. I meant to mention first that mole can be abbreviated MOL. All right, so 1 mole of N2 is what I'm given. And my goal is to get to atoms of N. So in order to do that, we need to start with moles of N2. And if I just wanted to get to atoms of N2, I could use immediately Avogadro's number to get to atoms of N2. But do I want atoms of N2? No, N2 is a molecule, right? I want atoms of nitrogen, atoms, not molecules. So I have another step first. So first, I need to convert to moles of nitrogen. Moles of nitrogen by itself. And then I need to get to atoms of nitrogen. And just stick with me. We'll see how this works. So that's my general problem solving strategy. So let's see how this works. So we've got 1 mole. We're going to start with what we're given. 1 mole of N2. That's what we start with. And I know I'm going to need to use these equalities. And let me clean this up a bit. I'm going to need to use these equalities here to convert to atoms of nitrogen. So if I start with 1 mole of N2, I know that in every mole of N2, there are 2 moles of nitrogen atoms. How did I know that? Well, remember, in 1 mole of N2, there are 2 moles of nitrogen atoms. Okay, so I'm starting here, and I'm trying to get to here in this first step. So, what is going to go on the bottom? Moles of N2 or moles of N? Yeah, moles of N2, right? Because I want to cancel them out. So using just this equality here, we're going to put 1 mole of N2 on the bottom and 2 moles of N on the top. All right, so I have done this step. Now I need to do this next step, and we'll do this one in blue. I want to get from moles of nitrogen to atoms of nitrogen. Moles of nitrogen to atoms of nitrogen. What do I know that connects moles of one thing to atoms of another thing? Yeah, Avogadro's number, right? Avogadro's number. So we can put, what are we going to put on the bottom? Moles or atoms? Yeah, moles. So 1 mole of anything, in this case nitrogen, is going to equal 6.022 times 10 to the 23rd, and let me give myself a little more room here, atoms of nitrogen. 6.0, because 1 mole of anything, cats, dogs, nitrogen, is going to be 6.022 times 10 to the 23rd atoms, molecules, ions, whatever you're trying to get to of that thing. Okay? All right. So, again, right? I started with what I was given, which is that I'm starting with 1 mole of N2. And I wanted to get to atoms of nitrogen. I can't go straight from moles of N2 to atoms of nitrogen because I got to use this ratio first. How many moles of those atoms are in 1 mole of my nitrogen molecule? And then I can get from moles of that thing, my moles of nitrogen, to atoms of nitrogen. And I promise this will get easier as you keep practicing. So I want to just reiterate, this is what I was given. This ratio came from my chemical formula. And this is Avogadro's number. All right, so now we got to carry out this calculation. So it looks like I have a bunch of numbers being multiplied and then dividing by, it looks like 1 times 1, so that's just 1. So we're just going to multiply the top numbers, which is going to be 2 times Avogadro's number. So 2 times 6.022 times 10, caret 23, and that's going to give us 1.204 times 10 to the 24. And then don't forget to say what you have, right? Put your units in there. We cancel out these ones, right? And I meant to cancel those out before. And we're left with atoms of nitrogen. So we have to write atoms of nitrogen. That's what I was looking for. Now, I always do a final check as well, right? This number is it a big number or a small number? Yeah, it's a big number, right? Very big number, which makes sense because we were looking for the number of atoms there's always going to be really, really, really large amounts of atoms in even a very small amount of a substance. Okay, because atoms are so tiny. So this makes sense. This checks out. So I would guess that that's probably correct. All right, let's try this again. So ethanol has the molecular formula C2H60. So right away, we have a little bit of information here. So we've got C2H60 is our formula. And then this says how many atoms of hydrogen are in 1 mole of ethanol. Okay, so 1 mole of ethanol, C2H60, equals how many atoms of hydrogen? That's our question, right? That's our goal, is to get to atoms of hydrogen. So let's kind of think of a problem-solving strategy here. So I start with moles of C2H60. I know how many moles I have. It's telling me I have 1. Okay, and now I want to get to atoms of hydrogen. Can I go straight from moles of ethanol to atoms of hydrogen? No, right? I have to go through moles first, because I have to get from moles of ethanol to moles of hydrogen, and then I can get from moles of hydrogen to atoms of hydrogen using Avogadro's number. So I'll say that again. So we're going to scooch this over I'll show you why. So we need to get from moles of ethanol to moles of hydrogen in order to get from moles of hydrogen to atoms of hydrogen. So that's our general problem-solving strategy. Now, how are we going to get from, one step to the next? Well, to get from here to here, I know I can use my chemical formula, right? That says that chemical formula tells me how many moles of hydrogen are in 1 mole of C2H60. How many moles of hydrogen? Yeah, 6, right? Because of this subscript here. So 6 moles of hydrogen. So I know how to get there using my chemical formula. Now, to get from moles of hydrogen to atoms of hydrogen, how am I going to do that step? Yeah, I'm going to use Avogadro's number. Avo's number. And sometimes I like to call him avocado or Avo. It's just kind of fun. So Avo's number. Using his number, right, we can go from moles of anything to atoms of that thing. So let's start to kind of solve this. Let's try this out. So we're going to start with what we're given always. 1 mole of ethanol, C2H60, this funky looking thing. And then I know I'm going to have to multiply by some factor, some conversion factor. So do I want moles of hydrogen or moles of C2H60 on the bottom? Yeah, ethanol, got to go on the bottom, okay? How many moles of ethanol? Yeah, 1 mole of ethanol, because in 1 mole of C2H60, we know that there are 6 moles of hydrogen. Okay, in 1 mole of ethanol, we know that there are 6 moles of hydrogen. That's what our chemical formula tells us, right? All right, now, next step. Now we can cancel out those moles of ethanol, and we're left with moles of hydrogen, which is great because now we're here. And now we need to go 1 more unit conversion. We need to say, all right, now I know in 1 mole of hydrogen, putting that on the bottom so I can cancel it out, right? In 1 mole of hydrogen, there are 6.022 times 10 to the 23rd, never give myself enough room, atoms of hydrogen. And now, remember, top right of your fraction or of your conversion problem is always what you are left with. And that was our goal. So we've got to do this calculation. So it looks like, remember with these, you're going to multiply everything on the top and then divide by what's on the bottom. So we got 6 times 6.022 times 10 to the caret 23. And that's going to give us 3.61 times 10 to the 24 atoms of hydrogen. Now, again, right, just a quick double check. Is this a big number or a small number? Yeah, big number, right? Because we're looking for atoms. Atoms are really tiny, so we would expect to have a really large number there, and we do. So we did it right. All right. One more practice problem, and then I'll let you go. So this says, how many molecules of water are in 2.4 moles of water? How many molecules of water are in 2.4 moles of water? Now, this is actually a little bit of an easier question than this one. I know it doesn't seem like it because now we're talking about molecules, but it actually is. It's less steps. So let's think of this, right? Remember, Avogadro's number, so far we've only been kind of figuring out how many atoms we get to. But this number can also tell you how many molecules you have, right? 1 mole of anything is 6.022 times 10 to the 23rd of that thing. So we're going to start with what we're given, which is 2.4 moles of H2O. Always writing what type of atoms or compounds I have right here, right? So 2.4 moles of water. And then I know I'm going to have some conversion factor here. Now, what needs to go on the bottom in this conversion factor in order to get to molecules of H2O? Do we need to put this number or this number? Yeah, the left, 1 mole. 1 mole of what? H2O, yeah, 1 mole of H2O. So what goes on the top? Avogadro's number, 6.022 times 10 to the 23rd. Is it atoms of water? No, right? Water's not an atom. It's a molecule, right? So molecules, and you can abbreviate molecules MOLEC. I think I've mentioned that before. But you don't want to, remember, don't confuse these. Molecules is abbreviated MOLEC, and moles are abbreviated MOL. Okay, so they're different. Okay, so now we have moles of water in our numerator and moles of water in our denominator, and we can cancel those out. So we're left with molecules of water in the top, and that was our goal. That's what we wanted to get to. So actually less steps, right, than something like this. Okay. All right, so let's see. So we got to calculate this out. So it's going to give us 1.44 times 10 to the 24. Actually, this should be 1.45. Molecules H2O. Again, big number, right? Molecules are pretty tiny, so we would expect some kind of large number at the end of this. Okay, now, if you were going to try to report this to the correct number of sig figs, how would we do that? So the convention is that we consider Avogadro's number exact. So this here is an exact ratio. Okay, so this is our only measured value. Measured value. So when we're looking at sig figs for this answer, how many sig figs should I have in this final answer? Yeah, 2, because there's only 2 in our measured value, right? And we're multiplying or dividing, so we take the lowest number of sig figs. So this should actually be 1.5. 1.5. Okay, and now you've expressed that with the correct number of sig figs. And let me actually write that down. 2 sig figs there, so 2 sig figs here.